Hey everyone, welcome this week to our regression lecture. This one's going to be a little bit different than what we've done in the past. This week we'll actually kind of depart from our traditional hypothesis testing steps that we've been using, and we'll learn to do something new. So this is going to be called regression. By the end of this unit, there's several things that I want you to be able to do. I want you to be able to determine when to use linear regression. I want you to be able to explain the differences between linear and multiple regression. I want you to explain what regression is and how it is used in the real world. I want you to be able to calculate the regression equation. I want you to be able to calculate the slope of a line, calculate the y-intercept. I also want you to be able to explain how correlation is related to regression. I want you to be able to calculate the predicted value of y given the appropriate information. So these are going to look a little bit different. Remember, when studying for this class, make sure you're using these unit learning objectives and creating yourself your own tests to practice whether or not you're understanding and being able to do these things by the time we get to the end of this unit. All right, let's go ahead and get started. So regression. We use regression when we want to predict things, and regression is actually, it's a whole class in itself. So although we're going to start to learn about linear regression in this class, if you continue on in graduate school of some sort, likely your next class will either be a class over ANOVAs or a whole class over regression. All right, so there's many different types of regression techniques. There's linear regression. There's something called multiple regression. There's also something called logistic regression. So at least for this class, when we're doing regression, we're not following our typical hypothesis testing steps like we've been doing throughout the semester so far. We're just going to create a regression equation. There are ways to test this with the hypothesis testing steps, but with how complicated it is, I'd rather just give you a primer for what it is and how we'd create this regression equation than to make us go too far in depth in it. All right, so linear regression. This is a statistical procedure where we can predict a person's score on an outcome variable from a score on a person's predictor variable. So this is going to be really brand new. What we've done so far is we've had where we looked for significant differences. So we did that with the one sample z-test, one sample t-test, independent samples t-test, dependent samples t-test, and our ANOVAs. We also learned last week about correlation, and we'll kind of continue to use our foundation in correlation to do regression. And so that's where we're trying to find a relationship. That's a different type of function of doing some of these statistical analysis. With regression, it's its own beast. We're trying to make predictions. So to do this analysis, the outcome variable and the predictor variable both need to be linearly related to one another. In other words, these two variables need to have a strong Pearson's R. And if we were to build the scatter plot like we did with correlation, we'd see that they have more of a straight line than a curve type relationship with it. Right, so for example, there is a high correlation between high school GPA and first year college GPA. So how might we want to use this information? We could use this information to create a regression equation. So if we were at college and we knew that there was a high correlation between high school cumulative GPA and first year college GPA, we'd want to collect all the cumulative high school GPAs that we could and all the first year college GPAs that we could, so that we could create something called the regression equation. Okay. So wait, you're telling me that statisticians can predict the future? And I am, absolutely. However, even with every prediction that we have, we're going to get some element of error. Okay. So now, unless those two variables have a perfect direct or a perfect indirect correlation, this prediction won't be perfect. So remembering that with a correlation of +1 or -1, that means the variables are perfectly correlated with one another. So if it was a perfect prediction or if it was perfect correlation, we'd be able to make perfect predictions, but we'll never have that happen usually in anything that we're doing. So would you want to use linear regression with two variables that don't have a statistically significant Pearson's R? Let's think about this a little bit. If we go back and think about the information we learned about statistical significance, what does it mean when we have statistically significant results? Answer out loud before moving on. This is how we study. It means that you likely got the results due to something other than chance. Okay. So we go back to the question, if we would do a linear regression with two variables that are not significantly correlated, the answer is going to be no. Okay. So multiple regression, this is a statistical procedure where we can predict a person's score on an outcome variable from a person's score on more than one predictor variable. So to do this analysis, the outcome variable needs to correlate with each of the predictor variables individually. But the predictor variables cannot actually correlate highly with one another. And the reason for this is because if they correlate highly with one another, they don't add anything new to the prediction. So we might as well just make it simple. All right, so multiple regression, example 1, admissions requirement. What do schools usually require for admission applications? Think about that for a minute. If the school uses more than one predictor variable, for example, entrance exam, previous GPA, number of extracurricular activities, then they would use a procedure known as multiple regression. Again, when using multiple predictor variables, you do not want those variables to be highly correlated with one another, but you do want them to be highly correlated with the outcome variable. So you could use these predictor variables to predict first year college GPA, which is really important for several reasons. So I don't know how much you all know about how much the college students here actually pay for how much it costs to educate students. But I think I heard a stat once that our students typically only pay about 75% of the cost that it actually costs to attend our university. And so with that, we get a lot of donations, and we have entire areas of the university dedicated to getting donations so that we can put that money into scholarships, so that students can come here and be educated and find a better way of life. We actually have one of the lowest rates of tuition in the state of Missouri because we believe that tuition and education should be accessible. And yes, I know it's expensive, but it actually, what we charge students doesn't end up covering the cost of educating each student. All right, so the reason why admissions might want to use predictor variables is in situations like this where the university is investing in students and in their future, they want to make sure that they're giving these opportunities to students that are going to be successful in school. So another example of that multiple regression could be used for is UCM previously, and I don't know if we still do this, used to use variables such as socioeconomic status and GPA to predict the level of risk that a first year student wouldn't return for a second year, which I think is really, really, really interesting. So why would UCM want to predict who's at risk for not coming back to the school the next year? If you said so that they could reach out and try to develop interventions so that we can keep a student enrolled here and successful, you're correct. And there's so many really cool things that regression can be used for. This is how they create weather models. People especially get really frustrated in the Kansas City greater metropolitan area because they say the weather is really unpredictable. And they did a study because a lot of cities will be like, if you don't like the weather, just wait a little bit. But they actually did a study across the United States in the major metropolitan areas. And Kansas City was rated the number one city for the most unpredictable weather in the United States. Right. And so if you get really frustrated with weather people not being able to predict what the weather is going to be, that might have something to do with it too. All right, so we're going to modify our hypothesis testing steps. You don't need to memorize these steps. This is just to walk you through because we're not going to do the full picture with linear regression. All right, so step 1 for this is we're going to determine which statistical analysis we want to run. That's typically what we do, and for all of our hypothesis testing steps. And we will do that with this as well. So linear regression, we use this when we want to predict a person's outcome variable from a score on a person's predictor variable. For this, because we're not technically doing the hypothesis testing steps, we're not going to write hypotheses. You definitely can do these things for regression. We're just not going to do it in this class. But we will go ahead and talk about our assumptions. Okay, so there are some assumptions with linear regression. The first one, I bet you are so shocked about, but both our predictor and outcome variables must be measured on a scale. What's a scale again? A scale is data that's on an interval or ratio level of measurement. So you'll see here we have the assumption, if we violate that, if our data is on a nominal or ordinal level of measurement, linear regression is not robust to the violation of this assumption. What that means is that then you would have to go in and find a different analysis to use to analyze your data set. The second one is that there's a linear relationship between the two variables, or predictor and outcome variables. You can check this by creating a scatter plot like we learned. You can also do this by checking a Pearson's R. If there's not a linear relationship between our two variables, then we cannot run this analysis. So it is not robust to the violation of this assumption. A third assumption that we have is the independence of observations. So this is where one participant's observation does not impact another participant's observation. If we violate independence, just like our other analyses that we've learned so far this semester, this analysis is not robust to the violation of this assumption. So then we have a fifth one, for significant outliers. So if we're looking at this, if a score has a z-score of plus or minus 3.29 or beyond, it's a significant outlier. And we cannot run this analysis with the outlier in it, but it is robust if we remove the outlier prior to running the analysis. And so if that happened, remember, we don't just remove data to remove data. If this happened, then you would need to write in your paper that you're writing your results in that you removed however many outliers and why you identified them as outliers. Although I've taught you this plus or minus 3.29 z-score criterion, there are other ways that you can identify outliers as well. So you want to make sure that you write in your paper why you did that. And then our last one is random sampling. And this is that we select our sample from the population of interest using random selection. And this is okay as long as we're careful about generalizing our results to the population. And then we list this limitation in the discussion section of our article. So this is pretty common. We've seen most of these before. These are slightly different because they do kind of run in with what we're doing with linear regression. So like homoscedasticity, that fourth one, where the variance of the residuals is constant across all the values of the independent variable. We would test for that by making a special scatter plot. You would just do that using a software. And so this one's kind of similar to our homogeneity of variances that we had previously, but this is more dealing with our regression line and the variance with that. And so a lot of the stuff that we would do with linear regression, we'd actually use some software to do this analysis, because some of these are actually kind of scary, but these assumptions are things that we've done before. They're just different takes on it. And so you could actually do this in Excel. And if I were going to make you all actually calculate these things and not just learn about it, I would probably actually have you do these calculations in Excel, because it gives quite a bit of information that we don't get elsewhere. All right, step 3 for this analysis is we're going to create a regression equation. Remember, we're not doing the hypothesis testing steps, although you could with linear regression. Okay, so in linear regression, you take two highly correlated variables and create a regression equation. You use the regression equation to make predictions about performance. So in order to do this, we need to remember some things that you may have learned a long time ago. So from back in the day, you may have learned a formula called y equals mx plus b. This formula was called the equation of a line. And so if you were trying to graph a line on a coordinate plane, you would use this kind of formula to figure it out. So again, you probably learned this as the equation of line. We're going to use this in statistics to create something called a regression equation. However, in stats, we write our equation just a little bit differently, and we use different symbols. So you'll want to write these symbols onto your symbol sheet. So the equation for regression will be the predicted value of y. So y with that apostrophe next to it is called the predicted value of y. So you want to put that into your symbol sheet. Lowercase b is going to be the slope of the line. And then a is going to be our y-intercept. So again, this can be a little tricky because in this equation, a stands for y-intercept and b stands for slope of the line. And that kind of goes in complete conflict with what we learned back in the day. And it's really interesting because even though we have y equals mx plus b in America, that actually isn't the same equation that people use worldwide. So there's a few different ones that mean the same thing. Okay, so if we're going to review some of these things a little bit, y-intercept is where the line crosses the y-axis. Okay, so the slope of the line is how much the y increases for the change that we see in x. A lot of times we see this as slope written as rise over run. So y with apostrophe is also known as y prime. And y prime is a predicted value that we get from doing the math computations with the regression equation. So remembering, the better that the correlation between our x and y values, the better our prediction is going to be. So to find the slope, we see here that we have slope equals, and it has a lot of wildness there for you. You have to be really careful with this formula for a number of reasons, but one of the main reasons is there is a ton of summation symbols, and the way they are used are very different values. So if we have the summation of x squared, that's a very different value than open parentheses summation of x close parentheses squared. And so using this formula, you have to be very, very careful that you're not making like calculation errors or just simple composition errors. So you'd put all these values in. So, we'd have x value, which is our predictor variable. Our y outcome is our outcome variable. And we take our x value times our y variable for each of the individual ones, and then we'd add them up, and that's how we get the summation of x, y. Then we take the sum of our x values and multiply it by the summation of the y values. After we add or we multiply those together, we divide that by our sample size. And then so once we work this out, like if you take it step by step, it's not a problem. It's just making sure that when you're doing it, that you're writing out all your steps. However, if you're actually to the point where you're doing this, most of the time, you're probably just going to be using computer software to do this, to be honest. All right, so let's compute A, which is our y-intercept. This one's a lot prettier and easier to do. So that equals the summation of y minus our slope times our summation of x, and divide all of that numerator by our sample size. So to do that, we're going to plug in some numbers. So after you find the slope, which is b, and the y-intercept, which is a, then you'll plug that information into our formula. So here we see we have y prime equals bx plus a. And then all you have to do to be able to find these predicted values of y is to plug in whatever x value it is. So if you have an x is 5, you'd plug in that 5 value where x is. You're already going to have the slope from the formula that you already used. You're also going to have your y-intercept already, and you would use all those values to find those predicted values of y. Okay, so your regression equation would look something like this. Y prime equals 1.5x plus 7. So this means you will not plug in anything for y prime or x at this point. You just get the regression equation first. So then when you want to make a prediction of y or y prime from an x value, all you have to do then is plug in that x. So if x is 10, you could find really quickly that 1.5 times 10 is 15. Plus 7 is 22. So if our x value is 10, our predicted value of y would be 22 with this formula. All right, and so I have another one here. For example, if we want to find the predicted value of y when x equals 5, you plug that 5 into the formula and you work it out. All right, so that's what our regression equation formula looks like. Then after that, you're going to calculate residuals and standard error of estimates. So the difference between the actual score of y and the predicted score of y is known as the residual. The residual provides us information on how big the error was in our prediction. So we can use that to calculate something called the standard error of estimate. This is a really scary symbol. Okay, so the symbol for the standard error of the estimate is S, which stands for, if you remember, standard deviation, right? So this is basically finding the standard deviation of the error that we see in the residuals, right? So our y value minus our predicted value to see how much error there is. And then we find the standard deviation of all those residuals, and that gives us the standard error of the estimate. So we have a formula here for that. It's pretty straightforward. We find our standard deviation of our y values. We multiply that by the square root of 1 minus r squared, and that will give us our standard error of estimate. So this is a really interesting analysis. There's a lot more to it where you can test to see if your slope is statistically significant, which means it predicts better than not having a predictor. And you can also test statistical significance of our y-intercept to see if it's significantly different from 0. And then you could do that, or there's another complete other way where you could use the ANOVA to do it. I'm more interested in that you understand what it is, what these different parts of regression are, so that you can understand it. So if you go on into school, you can use these as a foundation for it. That's all for this week. I know we're getting close to the end of the semester. It's been really nice meeting some of you in, Google Meets or Zooms or in-person office hours. And as we move toward the end of the year, it seems like meeting more and more people, which is not uncommon. Just hold on or hold in there, and we're almost to the end of the year. You're doing great. Have a great week.